Alright, let's start the fourth lecture of the series. And as we talked in the last class, that we will start with the nth root of 1, that's unity. And by the end of this class, you will understand and realize that why studying this thing is very important for studying the roots of any complex number. Alright, so as we said in the last class, that we will consider 1 as a complex number. So let us start with the representing 1 as a complex number. So how can you represent 1 as a complex number in the form of in the polar form? Then 1 can be represented as cos of angle 0 plus I sine angle 0. So you can see that it will definitely give you 1. All right. Then if you followed the last class, you can see that the nth root of 1 written in this fashion can be written, the roots can be written in the form omega k equals to cos 2k pi by n plus I sine 2k pi by n. As there is no theta, that theta is 0 here, so we don't have to put plus theta here. For any general complex number, we have to put plus theta and also a modulus factor over here. So 1 has modulus 1, so we don't have to put any modulus out here. We just write down omega k to be cos 2k pi by n plus I sine 2k pi by n. Pretty simple, where k runs over 0 to n minus 1. Now, it follows from the last discussion. So far there is no such things. All right. Now, this complex number is purely real. Now, when it will be purely real? Now, when this guy, this imaginary part, sine 2k pi by n will be 0. Whenever this sine 2k pi by n is 0, this value 2k pi by n will be, this cos 2k pi by n will be purely real. Okay, so when sine 2k pi by n will be purely 0, will be 0 when 2k by n, this guy is an integer. So in that case, if this 2k by n is an integer, then this will be sine into some integer value of pi, some multiple of pi, integer multiple of pi, and you know that sine of pi, sine of 2 pi, 3 pi, 4 pi, they are all 0. And in those cases, this imaginary part will vanish. So this number will be purely real if 2k by n is an integer whenever k belongs to 0 to n by n. Of course, k has a limitation between 0 to n by n minus 1. Now, note, when this guy can be an integer, when k is 0, definitely it will be an integer. This will be a 0. This will be 0, definitely. And it will be an integer when k is n by 2. Okay. Now, k takes integer value and n by 2 can be an integer, may not be an integer, depends on the value of n. So when n is odd, you may not get n by 2 as an integer, so k cannot take that value. So for n is odd, when the value of n is odd, then the only possibility when 2k by n is an integer is for k equals to 0. And in that case, if k equals to 0, then you get the value 1. Okay, 1 is definitely an nth root of 1, you know. And when n is even, you can definitely get an integer value over here. So you can have two different values for k, for which this guy is an integer. And in that case, for k equals to 0, you're getting 1. And for k equals to n by 2, in that case, you will get minus of 1. Okay. Because, why? Why this will be minus of 1? Because if n is n by 2, that means an integer, then this guy will be some multiple of pi, sine some multiple of pi, and this will be 0. But cos some multiple of pi will be minus 1, because cos pi is minus 1, and some multiple of pi will also be minus 1. Okay, and it will, okay, all right. So for k equals to 0, you are getting 1, and for k equals to n by 2, you'll get minus 1 as one of the root. Now just remember the cubed root of 1. If you remember the cubed root of 1, you must have seen that the roots are 1, omega, and omega square. 1 is, so cubed root 3 is odd. So that means you are getting only one real root, that is 1, and omega square. If you try to find out the fourth root of 1, then you will definitely see that the roots are 1, minus 1, and 2 other complex roots. Okay, so let us look at the picture. As we have seen in the last picture, that the roots lie on a circle. So here also the same sort of picture. This radius of the circle is definitely 1, because even the roots have these roots, they have modulus 1. So this circle is of radius 1, and this first alpha is the first principal root. That means this is the first root definitely for k equals to 0. For k equals to 0, you are supposed to get the principal value. That means theta by n. Okay, if you remember, for k equals to 0, you are supposed to get the principal value. If you remember from the last lecture, let me show you the last picture also. So for k equals to 0, you are supposed to get theta by n, and in this case theta is your 0. So for k equals to 0, you're supposed to get an angle 0. So you'll get 1. That's the principal value. So 1 here for the unity, for 1, the nth root, 1 is the principal value. And then 2 pi by n angle. So this is the first one, 2 pi by n. Then twice of 2 pi by n, then thrice of 2 pi by n, 4 times of 2 pi by n, and so on. Now, if you keep on rotating, if n is odd, then you will never come here. If n is even, then there will be a value that will fall over here, and that will give you minus 1, and they will keep on rotating till just bottom of the real axis. So they are the roots of 1, the roots of unity. Okay. Now there are certain properties of these roots, the roots of unity. All right. So if you take k to be, you know where k is running from 0 to n minus 1. Okay. Now let us take k to be n minus r, where r is running from 1 to n. Now what is happening over here? So it is nothing but if n r is running from 1 to n, then n minus r definitely lies between 0 to n minus 1. So it will be 0 when r is n, it will be n minus 1 where r is the smallest possibility 1. So definitely there is no problem with this notation. K is n minus r where r runs over 1 to n. Alright, now let's look at this guy, omega of n minus r. So how to get this? You just put the value of k over here to be n minus r, and you're supposed to get something like this. A simple modification or calculation will show you that the value will turn out to be this thing, which is the conjugate of omega r. Okay, now omega is r is also a root because r is lying between 1 to n. Okay, all right, I have made a mistake over here. You're not supposed to get a conjugate of you have to omit n over here, so I'll just okay, that's a mistake I made. All right, I'm sorry about that. So r is not supposed to go to n, so we are not talking about the real root, we are talking about the purely imaginary roots of 1. Okay, so you're supposed to consider the r to be strictly less than n. Okay, I'll change it in the lecture note, and in that case you are supposed to get only the purely imaginary roots. That means the roots that are not on the real axis. So in that case you are just take the essence of it. Omega of r is nothing but omega of n minus r is the conjugate of omega r. All right, it shows that if you omit k equals to 0 and if you take k to be r, the value that you're getting for k equal to r is the conjugate of the value that you're getting for k equals to n minus r. Okay, that's what it says. Omega n minus r is the conjugate of omega r. And mind that it's a mistake that I made. It will be r strictly less than n. We are not considering k equals to 0 case. Okay, all right. Right. So that means we are actually pairing the roots. So we are pairing with omega r and omega n minus r together. Omega n minus r is the conjugate of omega r. So in a reverse direction, we can also say that omega r is the conjugate of omega n minus r. If you take conjugate on both sides, you will see that it will be omega r and it will be omega r n minus r conjugate, because so we are conjugating them, the two numbers. So omega r is the conjugate of omega n minus r. So let me show you this picture over here. It will tell you the actual thing. Suppose you start with an odd number n to be 7. So you just omit k equals to 0 case. That's what we are saying, that the mistake that I have made, that we are not considering r to be n. If r to be n, then we are also considering k to be 0. So we are not considering k to be 0. We are only considering the k to be 1 to the 6 in this case, because n is 7. This part only. Okay, we are pairing these values, the roots corresponding to these values of k. All right. If you take k to be 1, that means we are considering omega 1. That is the conjugate of omega 6. Right? Why? If you take k to be 1, if you take k to be 1, that means n minus r uh, is 1. That means r is n minus 1. Okay, if it k is 1, then r is n minus 1. Is that clear to you? I hope. Then if it's k is 1, then r is n minus 1. That means 6 here. So you are pairing 1 with 6. These two are conjugate to each other. If it is k to be 2, then it is conjugate with corresponding to this guy. If you move one here in this direction, then you have to come back here, one here. Then these two are conjugate to each other, and these two are conjugate to each other. All right, for n to be odd. So for n odd, omit the case k equals to 0, the principal case, that is the one value, and the other roots, they are all purely imaginary roots because there is no minus 1 for the case of when n is odd. So we are basically pairing the complex roots as conjugate to each other. For this one is conjugate to the last one, this one conjugate to the second last one, and these two here. So if there are more points, you can see that you can actually conjugate them to each other because they can be paired two together because it is odd. So there will be n values for k. So if you omit 1 for k equals to 0, then you will be left with the even values of k, even number of points here. So you can conjugate them, you can pair them two together, r and n minus r. All right. And the last one, you can see this is 3. Now 3 is what? 3 can be written as 7 minus 1. I will come to that. Okay, let's not do that. In the case of even cases, as we have already seen, that even cases have two real roots corresponding to k equals to 0 and corresponding to k equals to n by 2. So for even case, n is 8. So there will be two real roots for k0 and k4 plus 1 and minus 1. We just omit them and the rest of the roots will be complex, and the complex roots are conjugate to each other in they are paired in this fashion. 1 is paired with the last one, 7, 2 is paired with 6, 3 is paired with 5, almost like that. I mean, if you take more values of 8, then you can have more such pairing. All right, now what I was saying is here. So for n odd, so how many pairing you can do? So for n odd, k equals to 0 case is your 1. So we are now rewriting the roots of 1 in the light of this pairing. So for k equals to, for n odd, we can have 1 as one root for k equals to 0, and the other roots are paired in this fashion, that the first one, as I said, this one is the pair, this is the conjugate of, sorry, this one is the conjugate of this one. So the value corresponding to k equals to 1 and k equals to 2, the one here is merely the conjugate of this one. So these two can be written as plus minus. So for k1, it will be 2k pi by n, and 2 pi by n and 2 pi by n. So there will be two roots, 2 pi by n plus sine I sine 2 pi by n, and the other root, this one, will be 2 pi by n minus I sine 2 pi by n. So that's their conjugate. So they are paired. So, and the last one, this one, is what will be this one? The last pairing. Last pairing is, in the case of odd, you can write them as n minus 1 by 2. So 3 is merely 7 minus 1 by 2, as you can see. Okay. In the even case, there will be two real roots. If you just omit the two real roots, other roots are paired in this fashion. And how many pairing is done? The pairing will be n by 2 minus 1 cases. All right. So I would suggest you to look at this matter yourself and think over it. You know, it's very difficult in this way to make you understand. Rather, you will look at the small examples and see that how this pairing and how this is written. So here we are basically writing the roots in the lights of pairing. The pairing is here. Only the one small change that we have to omit, this equality sign over here. R will be strictly less than n. And as we have the roots like this, so next let us do something more about the roots of unity. At this point you have to, I don't know whether you have already learned it or not. Anyway, it is there in your syllabus. You will learn it in future definitely. So suppose you start with an equation, a real equation, x to the power n equals to a, where a is a real number, n is an positive integer. An equation like this, then it has how many root it has? It will have n roots. So suppose alpha 1, alpha 2, alpha n be the n roots of a n degree equation. You must have heard this thing that any n degree equation has n roots. 2-degree equation has 2 roots. I mean quadratic equation has 2 roots. Cubic equation has 3 roots. Similarly, any n degree equation will have n roots. So suppose alpha 1, alpha 2, alpha n are the n roots of this equation. Then this guy x to the power n minus a can be factorized in this fashion. X to the power n minus a can be written as x minus alpha 1 into x minus alpha 2 into x minus alpha n as n factors. Okay, and I whether I don't know whether you're familiar with this notation or not, but you have to be familiar with this notation. This notation is called the product notation. It means, this notation actually means this. It is similar to the summation notation. You must have seen the summation notation. So if there are many things similar to each other, then it can be written in this fashion, where p is the running index and p runs from 1 to n. This means, this guy actually means this thing. You keep on putting the values of p and keep on putting the factors. For p equals to 1, x minus alpha 1 into x minus alpha 2 into x minus alpha 3. This is similar to the summation notation, and this is called the product notation. All right, fine. So now, why we are discussing this? Because we have an equation of this form, x to the power n minus 1. That's the basic, the fundamental equation of the nth roots of 1. So x to the power n minus 1 equals to 0. The roots of that equation you have seen first in a normal manner, then in the lights of this conjugation thing, the pairing thing, you have also noted down the roots both for n even and for n odd cases. Now we are looking at the polynomial x to the power n minus 1. Now this can be written in the form of product. Now what are the things? So if n be odd, in that case 1 is one of the root, so that will be one product, one factor, and the other factors are the roots listed here. They are other roots, so we will simply write them down, so in the product fashion. Okay, just get familiar with this. If you keep on putting k from 1 to this, you will getting all the things. So this is merely the plus one, and this is the conjugate one. The plus thing 2k pi by n plus I sine 2k pi by x minus that, x minus, this is the minus thing that has become plus over here. All right, now a simple a plus b a minus b thing will give you, a plus b into a minus b thing will give you square minus this square, and this square means I square into sine square of this, sine square of this. And if you a plus b whole square formula, if you put them, if you expand them, then I square is minus 1, you know, then minus 1, this minus will become plus, and 1 cos square thing will come, and that will give you 1, and this thing. So for n is odd, this polynomial can be factorized in this fashion. Okay, and for n is even, the similar thing, it can be factorized in this fashion. All right, fine. Now so far we have learned What are the things we have learned? We have learned what are the roots of 1, and then we have learned the rewrited the roots in the case of n to be odd and n even in both cases, and we have seen how to write the polynomial x to the power n as the product of certain real numbers. They are all real numbers. See, they are all real products, real factors, real polynomials. Okay, fine. Now, before we go to the application thing, we have to learn certain thing. We have to see. We have to uh, well prove also certain thing that you have already seen in your 10 plus 2 level. That's called De Moivre's theorem. Okay, what does it say? That the general form of De Moivre's theorem says if n is an integer, positive or negative, irrespective of that, and theta a real number, then this complex number cos theta plus I sin theta to the power n will be this guy. See, if you remember that we have already used it in the last class, and now we will be actually proving it. This is for the integer values, positive or negative. This is simple. And for n is a rational number. Rational numbers means, that's a fraction, positive or negative rational numbers. Then this guy is one of the values of this thing. There can be many values. This is one of the values of that thing. Okay, so first thing first. So let's do the, so how many cases that there can be? How many cases there can be? Case is for integer, positive integer, from negative integer, and the last one is for rational numbers. So case 1 is for n be positive integer, and the proof follows by the principle of mathematical induction. It's easy. You have learned principle of mathematical induction, and what it does, it says that you have to prove that some assertion for n equals to 1, that is to consider this for n equals to 1. For n equals to 1, this will be cos theta plus I sin theta to the power n, and that is definitely cos theta plus I sin theta. So for n equals to 1, it is true. Assume the result to be true for n equals to m. Now try to prove it for the result for n equals to m minus m plus 1. So what you have to do, you have to do that you put m plus 1 over here, and if it is m plus 1, then m plus 1 can be written as some this to the power m into this thing. That's a rule of indices, and that will prove. Then a bit of trigonometry will give you the result. You try to prove this. If you can't, then let me know, then I'll show you the proof. Okay, it's easy actually, and it follows from the mathematical induction, and I'm leaving it as an exercise just because you have to brush up your memories of mathematical induction also. So try it. If you can't, then I will definitely do it. Okay, so for n equals to positive integer, this thing is true. For n equals to negative integer, suppose n is minus of m. So what will be? If it is minus of m, then minus means it goes on the denominator, and in this case, as we know that m is a positive integer here, so this will be this, and the rest of the proof follows by a simple rationalization. Rationalization means, we have said that what is rationalization? That means you have to multiply by the conjugate of this guy at the denominator as well as the numerator. If you multiply this guy by the conjugate here, then it will be cos square m theta plus I square I plus sin square m theta, and that will give you 1, and on the numerator you will be left with certain things, and then some trigonometric result will give you the actual proof. Okay, I am also leaving it for you to do, because this is simple. There are certain simple things that you must try your hands on. Okay, now the thing is, when it is a rational number, that's the most important part. Now let's recall the definition of rational number. So if n is a rational number, then it must be of the form p by q, where p, q are integers prime to each other and q greater than 1. Why I am giving this q to be greater than 1? Because if q is 1, then n will merely be a real number, an integer, which we have already discussed. If q is greater than 1, then only it will be real fractional rational number. All right. And p can be positive or negative. Depending on p, positive or negative, n will be positive or negative. Okay, so we are not really bothered about positive or negative, because positive negative things in the case of integers are done separately here. Positive integer, negative integer. Now here, what we have to prove? We have to prove this guy is one of the values the of this thing, right? So let's start with this. Put raised to the power q, and as q is a positive integer, then it will go inside and will cancel out q, and we will be left with this. Then again, by the De Moivre's theorem, the first part of the De Moivre's theorem, the p comes out. Okay, now what we have, this is this. Now take both sides, the cubed root of both sides, and that gives this on one side and the cube root on the other side. Now why this one of the value thing comes here? Because this thing, whenever you take cube root of this complex number or this complex number, you are supposed to get q different values. Okay, in particular here, if you take the cube root of this complex number, you are supposed to get q different values. Okay, and this is merely one of the value of the q different values. You can actually say that what are the q different values? If you take the q root, then the q different values will be cos 2k pi plus p theta by q plus I sine 2k pi plus p theta by q, where q k runs from 0 to q minus 1. Okay, that's the range. That are the different values you are supposed to get, and this is the value that you are supposed to get for k equals to 0. That's the principal value, and there are other values. So that is why the theorem says this is only one of the values of the of this guy. Okay, so that is what De Moivre's theorem is all about. Now the next thing is actually the application of De Moivre's theorem and the roots of unity. This is the most important, interesting part, and here you will get the real essence of roots of unity and its importance for finding roots of any complex number. Okay, so first we will rewrite the roots of unity again with the suffixes. Let's omega k be this one for k equals to 1 to n minus 1. We are just fixing up a notation. Then further, let us denote omega to be omega 1. Then for any omega k, if you apply De Moivre's theorem, then k can be taken out, and we are left with this guy. And what is this? This is merely for omega k to be 1. So this is your omega 1, and omega 1 is omega. So this is basically omega to the power k. Okay. All right. So note that again, we are only dealing with the purely complex roots of the unity. We are not dealing with the root the root 1 and minus 1. We are only dealing with the complex roots. The complex roots can be written in this fashion. The the one that corresponds to k equals to 1 and then multiples of that. All right. Then the roots can be written as the corresponding to omega k equals to 1 is omega 1 omega, and any other for k equals to for any other values of k can be written as omega to the power k. So the roots of unity can be listed as omega 1 and omega omega squared up to omega to the power n minus 1. Now if you just think of the similarity of the cubed root of 1, what are the cubed root of unity? Omega 1 omega and omega square. Now also look at the similarity. What is the value of omega for cubed root? That can also be written as cos 2 pi by n plus I sine 2 pi by n for n to be 3. So in that case, that will be cos 2 pi by 3 plus I sine 2 pi by 3. And you know the value of cos 2 pi by 3 and I sine 2 pi by 3. Just put them and you will get the actual omega and omega square. That's the same thing that is written for n for larger indices. Now, the most important thing. Then, for any complex number z, you know the roots can be written in this fashion, nth root, right? So let us put it in this fashion. Any for k equals for any k, it is this into this. You know, if you multiply this by a simple trigonometric result, you can show that this will be this guy. Okay. Now, this multiplying means cos into cos this plus sine into sine this minus, that will give you cos of this thing, and then you take out I and whatever, the simple multiplication will give you this thing. The important thing is this lies here, and note that this is merely up to this r to the power n, and this theta by n, this thing, the one that I am showing is your this thing. Oh, sorry, only this part. This part is your the principal value of the nth root of complex number. This, just recall that, and you are left with this multiplied by another factor. Now, what is this factor? This factor is your omega k, and which is nothing but the omega to the power k. What is omega? Omega is the nth root of unity, the first corresponding to k equals to 1. Okay, so if you simply denote the principal value by z0, then you simply, the kth root is z0 into omega to the power k. So the for k equals to 1, it will be z0 omega to the power 1. That means omega. All right. And for k equals to 1, for k equals to 0, it will be the only this thing, omega to the power 0 is 1. Okay, so basically what is happening, it is actually starting with the principal root of z, and then the multiplication of other roots of unity is basically giving a rotational action to that root. So action of roots of unity to the principal root of any complex number gives a rotation, and this rotation will give you the other roots of the complex numbers. So to find the nth root of any complex number, it is enough to find the principal root and then multiply it by the nth roots of unity to it, and you will get the n different roots of z. Is it clear to you? That means looking at the nth root of 1, getting the set is very important because they will eventually give you other roots of the roots of any complex number. So for looking at the nth root of any complex number, that means this is sort of thing, you may just have to get the principal nth root. That means if you are starting with r cos theta plus I sin theta, you just have to write down r to the power n minus 1 cos theta by n I sin theta by n, and to this complex number you keep on multiplying the roots of unity. That means 1. If you multiply to 1 by 1 with this, you will get back 0. If you multiply omega to this, you will get the first rotational thing. That means this will be the first for corresponding to k equals to 0. And then this rotation, this 2 pi by n rotation, this rotating by 2 pi by n is merely multiplying by 1 of this omega. First time you multiply by omega, then you will rotate by 2 pi by n. Two times you multiply to omega to z0, you will be 2 times rotated and you will get this point. Okay, so that is how the roots of unity is associated with the roots of any complex number. Okay, so that is why this is important for you to learn about roots of unity. There are various examples and various results I will discuss, or maybe I will give it as an exercise and examples as in the lecture note. Okay, so I'm not discussing them. So in the next class we will be discussing the exponential of complex number and logarithm of complex number. Okay, that's all for today. Thank you.